week's speaker is Dr. James Wray, who is a professor in the School of Earth and Atmospheric Sciences here at Georgia Tech. His specialty is on using spectroscopy, particularly in the visible near infrared, to study the surfaces of planetary bodies, Mars and beyond. We're going to be hearing about both today, the Mars and beyond. He has an undergrad degree from Princeton, PhD from Cornell, and then he came straight here right after that. And what year was that?
2011.
In 2011. So he's been here for a long time. And I'm really happy that he's going to be updating us on what he's been working on more recently, which are these interstellar objects and how he's been applying, like I said, visible near infrared spectroscopy in trying to understand that. So thank you so much again. Yeah, the floor is yours.
Yeah, thank you. Thank you for the invitation. I've been here a few years now. I've given planetary seminars before, but it has been, I think, 4 years. The last time I spoke in the seminar equivalent of this was fall of 2020. So I thought I could focus on the types of things that I've been doing research-wise, my group has been doing in the years since then, which includes a lot of Mars geology, remote sensing focus. But also more recently looking at interstellar objects, so asteroids or comets that actually originated from beyond our solar system, but which we found briefly passing through it. And those seem like two very disparate subjects. And so I was trying to come up with a title that would sort of link them together, and was having trouble doing so. And so then one morning, alarm clock went off and I groggily stumbled into the master bathroom, as one does, and looked in our bathtub, and there was a sippy cup of milk in there, and like, how did this get here? And of course, any parents in the room know exactly how that got there. A newly bipedal miniature human is the answer. They always think they have better ideas than you of where things should go in the house. But then it hit me, that's the theme that sort of ties together the various projects that I want to talk to you about. How did this get here? And I think, as additional personal context, it is a question that people often find themselves asking at kind of the midpoint in life, which I guess I am now officially at. And, for this audience in particular, how did a guy from New Jersey, New York originally end up at a place like Georgia Tech, in part because that was there was a job available when I was coming out of graduate school, but also, I don't know, again, you try to sort of like make sense of your life at some stage. And another life event that happened, unfortunately for me in the past year, was my mom passed away. She still lived up in New Jersey. And we had to clean out her house, and there was this crocheted, thing of our last name that hung in the hall my entire life growing up. And so I took it off the wall to bring it down to our home in Atlanta. And when I took it off the wall and looked on the back of it, there's a sticker that shows that the frame for this was actually purchased about an hour east of Midtown Atlanta, and it has sort of opened my eyes to the fact that there's a significant portion of my ancestry that hails from northern Georgia that I sort of hadn't realized when I moved here. So maybe there's some sense to the story after all. But anyway, asking those kind of questions personally maybe has made me more interested in them scientifically as well. So I'm going to talk about a number of things that all at least sort of loosely tie into that same theme, starting with kind of the biggest campaign in planetary science for really the past couple of decades now, which is trying to bring back rocks from a particular location on Mars. That'll segue into some work we've been doing to identify volcanoes on Mars that had gotten missed before, even in some pretty conspicuous locations. And then I'll talk also about aqueous processes. NASA's always following the water on Mars, and some new insights there lately. And then I'll make an abrupt transition to interstellar objects. So if you're wondering what this image on the title slide was, I had to pick something, but this was while I was in grad school at Cornell. I was working with Steve Squires, who is the science PI for the Spirit and Opportunity rovers. And Opportunity in some ways was the luckier of those rovers. It landed in a sedimentary wonderland. Again, for years, NASA had been trying to find places with aqueous deposits from long-standing water on the surface, and it landed in this place that had all these light-toned sedimentary rocks for the rover to explore. And in fact, as the mission went on to many years of extensions, it almost got a little boring. All that was there was these light-toned sedimentary rocks full of sulfates. Yes, very interesting, but we'd like to see something else. And one opportunity to find something else came when the rover was traversing the plains from one crater to another and passed this rock. This is one of a few examples like this, which was a dark, relatively erosion-resistant rock, very different from the bedrock geology just standing loose on the plains. And how did that get there? Well, in a planetary context, often when something weird is observed, we say it must have been due to impact cratering, and that's probably the answer here, that there is some other part of Mars that has these dark-toned rocks, and there was an impact there that ejected a piece of that geology and brought it to this site for opportunity to kind of sample a different part of Mars, which was a nice opportunity to have. And we do similar things here on the Earth and have for many years, because sometimes impacts eject material all the way out of, beyond a planet's atmosphere, beyond its escape velocity. It traverses through interplanetary space and occasionally winds up here on the Earth. This was one of my first student advisees at Georgia Tech. Sheridan did some Mars remote sensing research with me, and then at the end of her graduate school experience, got a chance to go with the Antarctic Search for Meteorites team to look for such rocks, only a small fraction of which are from Mars, but some are. So yeah, we have pieces of Mars. You might then ask, why do we have to spend $10 billion to bring back more pieces of Mars, as NASA, I think, still wants to do? I'll talk about that in a minute. But the issue is we don't know how the particular rocks we have from Mars got here, or really more to the point, where they came from. We're missing the geologic context, and also we're probably missing some of the rocks that would be of greatest interest. Again, the sedimentary rocks are softer, so less resistant to erosion, both in normal processes on a planetary surface or in being ejected through an atmosphere and having to survive passage through another one to land here on Earth. So for some of the most interesting rocks, we probably need to handle them more carefully and bring them back from the sites of greatest interest. And so for as long as NASA has been doing decadal surveys of what should the priorities be for the next 10 years of planetary exploration, Mars sample return has been the highest priority. The first such survey was done in 2003. There's a separate Mars prioritization versus other missions, and the Mars panel said, we really got to return samples from Mars. In 2011, they lumped all the planets together and said the highest priority flagship class, most expensive type of mission is Mars sample return. And then just a couple of years ago, another decadal survey said the highest priority of anything in planetary science is we really got to finish sample return. But it's hard because we've never done what is depicted here in this. It's easy to make a PowerPoint slide with a rocket launching autonomously off the surface of Mars, but it hasn't been demonstrated yet. So we're in an interesting time at the moment relative to this effort, in that earlier this year, the NASA administrator came out and said, I don't want to spend what this is now projected to cost, over $10 billion for the total campaign, and wait until over a decade and a half from now was kind of the most up-to-date projection of when the samples would actually be returned to Earth under the architecture NASA was considering for this. So as of about 90 days ago, NASA gave funding to 7 different industry teams to tell them a better way to do it that would hopefully cost less than $11 billion and get samples back sooner than 2040. And we'll see what comes of that, I guess, probably in the coming days. But again, I feel like it's hard for NASA to entirely back out of this campaign, given how high a priority it has been for the planetary science community, or if you just want to go by, what got us to land humans on the moon. Back in the 60s, it was a space race, and just yesterday, China confirmed they're planning to return samples from Mars. It didn't say what the return date would be, but the date of launching the mission to do this would be just 4 years from now. So if nothing else, maybe another space race will motivate us to complete this campaign. Again, though, you might ask, why do we need to do this if, given how much we already know about Mars, and much of which we've been able to learn from remote sensing or just from landing on the surface and studying the rocks with instruments that we can carry to Mars. This is just one illustration of all that we know about Mars that is from a review paper that I've sort of helped populate some of these points over the years. So Sheridan Ackes, when she was working here with me, found these sulfate salts down here at high southern latitudes. A big part of my dissertation was populating these sulfate and some of the clay mineral points. Phyllosilicates or clay minerals are, I can use that. That's great, thank you. Basically all of these minerals that are shown here are things that have to, or at least we interpret they did, involve liquid water interacting with the rocks in order to form. And what has been great to learn over the past 2 decades is that there's this mineralogical evidence for water-rock interactions across a huge swath of the surface of Mars, but with regional diversity. Some places sulfates are more common, some places chlorides, some places carbonates. And so that really has motivated some of the landed missions to go and explore this diversity in situ. And again, I think, it's great to know that all of this is there, but we're kind of now at the point where we want to ask the next question: how did these get here? What was, in detail, why do you have clays here versus carbonates here? What were the processes? Because there's always a few different possibilities, and we'd like to start to distinguish between those. And so that was in part the motivation for sending the Perseverance rover to one of the densest concentrations of different aqueous mineral deposits in the Nili Fossae region of Mars, and in particular in a crater called Jezero. So this is the orbital remote sensing with the CRISM spectrometer on the Mars Reconnaissance Orbiter that showed both some primary minerals that you would find in igneous rocks like olivine, but also carbonates, clay minerals, even some hydrated silica in Jezero crater. And so the Perseverance rover was sent to a place where you also can see there is a nice sinuous channel that seems to empty onto the crater floor here, and a fan-shaped deposit of presumed sedimentary rocks that the rover could go investigate. And maybe you had lake sediments widespread across this crater floor for the rover to traverse across, was the thought, at least prior to landing. And so Perseverance landed there in spring of 2021. And this mission was the first step in at least thus far, has been planned as the first step in the sample return campaign for Mars. So in addition to studying the rocks with its own instruments, it's putting samples of them into these little containers and leaving them at locations on the surface, and keeping some on board that, one of these brilliant solutions to NASA's call for cheaper ways to return samples from Mars, I guess, is going to try to go and pick these up sometime in the next decade or so. The rover has actually surprised me with how rapidly it's collected samples compared to some previous rovers' rates of sampling on the surface of Mars. But some of the rocks that it has come across, I would say, were initially quite surprising. And the very first rock that the rover abraded with its grinding tool to look at the dust removed inner texture of had a crystalline igneous texture. So interlocking crystals of minerals like you would not see in a sedimentary rock. And really would not even see in a lava flow right at the surface of a cold planet like Mars. So that was pretty surprising. There are headlines like this, these rocks shouldn't be here. So how did this get here? And this finally motivated me to make good on something I had been thinking about for a number of years. As Jezero crater was suggested and prioritized and ultimately selected as the landing site for Perseverance. If you just take a step back and look at this crater in the topography here is what you're seeing in the colors. What stands out to you all as kind of, not something you'd see for just any old crater on Mars? Yeah.
It looks like there's a river going into it.
It looks like there's a river going into it, indeed. That was kind of the primary motivation for going there is you actually have arguably two channels feeding sedimentary fans in the crater, and then a third one that's interpreted to be an outflow channel, meaning that you filled up the crater with water that then overflowed. So that is all great for astrobiology type science. Anything else? Yeah.
Right bottom corner looks like a volcano.
Thank you, sir. The right bottom corner looks like a volcano. I thought so too, about 15 years ago. And here's an exaggerated perspective view, exaggerated topography that adds in another data set, which is the brightness in the infrared at nighttime observed with the Themis instrument on Mars Odyssey. So bluer areas are colder at night, and the orange yellow areas are staying hotter overnight, retaining heat better. So this is a proxy for so-called thermal inertia. And basically the point I wanted to make with this is that this mountain sitting on the southeast rim of Jezero crater looks distinct in its nighttime thermal properties, as well as it being a major topographic prominence. Its surface materials are retaining heat less well overnight than most of the surroundings. So we requested an official name from the US Geological Survey for this feature. It is now called Jezero Mons. Here's another view of it from sort of the southwest. Again, I first noticed this back in 2007, entered targets there to try to understand, is it a volcano? Is it's something else? I'll list a few alternative possibilities. But meanwhile, NASA wanted to land on the other side of the crater. And so every time we had an orbiter passing over this crater, we imaged the other side of the crater. And it took about 15 years to finally get some images of this feature. Meanwhile, we did land Perseverance there, and in its first panoramic view of the surface, you could see this Jezero Mons feature off on the far horizon. It's about 50 kilometers away because that's the width of Jezero crater approximately. The rover took a higher resolution panorama a couple months into its mission, and so you can get a nice topographic profile effectively of this feature from the ground, but you can't really see too much detail, and unfortunately, all the rover has done since this time is drive in the opposite direction, and that's probably all it's ever going to do, and I understand there's a lot of interesting rocks that way, so I don't blame them. But in the meantime, what can we do to understand this feature better? Well, the orbital assets that we have available actually have better resolution from 300 kilometers up than Perseverance had from 50 kilometers away. So with Dr. Rivera Hernandez in summer 2021, we advised an RAU student who took a look at basically all the orbital data sets available for this feature, including the CRISM and infrared spectroscopy data that allows you to map minerals across the surface. And so this is a context camera, the sort of medium resolution camera on Mars Reconnaissance Orbiter view, colorized with detections of various minerals on Jezero Mons, looking from the top down, which I'll just note, here is an explosive volcano on the Earth at exactly the same scale. And as I didn't even have to say it, as the audience here noted, looks strikingly similar, at least to me. So looking at the minerals across this feature, you can see a lot of pyroxene in the greens. That's an igneous mineral that you can get it, you can find it in sand all over Mars and various rock types, but it is at least consistent with an igneous construct like a volcano. Kind of interesting or weird to see some alteration phases, some evidence for water rock alteration, such as phyllosilicates up on this feature if it's a volcano. I'll note that one of the largest exposures of clays on the surface here is actually in the ejecta of a crater that maybe just penetrated through any volcanic materials to the underlying clay-rich material that we know is abundant in this region. That's why Perseverance went there. And then if you look around the edges of Jezero Mons, it's sort of interesting to see the contact with the underlying more clay-rich material surrounding it. So here you can see sort of an eroded margin of Jezero Mons that is dark bluish. And this is an image from another color orbital camera that I work with, sitting on top of the older clay-rich materials that were kind of the primary target for Perseverance. This is actually on the floor of Jezero crater, where it kind of looks like you have maybe a flow margin coming off of Jezero Mons extending onto the floor of the crater. So this is why it was of interest to me in trying to understand, where did these weird, surprising volcanic rocks found by Perseverance in Jezero crater, where could those have come from? So to try to better argue that this feature could be volcanic beyond just the eyeball test, we looked at some other similarly sized volcanoes that had been identified previously on Mars. A lot of the sort of first round of volcanoes found on Mars are large so-called shield volcanoes. They're low profile, effusive volcanic constructs like you find in Hawaii. And here's one example of those that's one of the smallest, so most comparable in scale to what we see at Jezero Mons. And then some inferred explosive volcanoes started to be identified around the turn of the century. Here's a couple of those. And then there was a paper just a couple of years ago that I actually found reassuring, because they're identifying explosive volcanoes that also had clay minerals on their surfaces. So it's like, okay, people think it's reasonable that you can, it's actually, they argue that finding the clays there at the summit of this feature supports a volcanic interpretation, because an explosive volcano makes very fine-grained glassy material that would be easily altered into phyllosilicates. So anyway, we with this RU student, Sarah, she compiled morphometric data for Jezero Mons and for all of these other Martian examples of roughly similarly sized interpreted volcanoes, and then also for the example I showed from Antarctica. And things to call your attention to, I would say, are especially this height to diameter ratio. The aspect ratio of Jezero Mons is identical to previously interpreted explosive volcanoes on Mars, as well as one here on the Earth. The quantitative thermal inertia, the degree of fine particles that are present, is also similar to what's previously been seen for explosive volcanoes. That's the opposite for, again, Uranus. This is a shield volcano that we couldn't get a good measurement of thermal inertia from, but actually in that case, it's hotter overnight than the surrounding terrain. So that shield volcano is probably made of coarser lava flows, as a shield volcano should be. So this sort of suggested to us that Jezero Mons has the most in common with explosive volcanoes, and we put together this sort of truth table to evaluate that hypothesis, the stratovolcano or explosive volcano versus shield volcano versus Some other possibilities are mud volcanoes are a thing that exists if you haven't heard of them. Sediment can erupt out of a cone similarly to how lava does. But those features, at least on the Earth, are always over an order of magnitude smaller than what we see at Jezero Mons. Other possibility, I guess kind of the null hypothesis that people have been assuming for all the time that Jezero has been mapped by people and this feature's been ignored, is that it's just an impact crater sitting on the top of an old hill. That seems unlikely to me, given some of the distinctive properties like the low thermal inertia. And also, if you count impact craters across the surface of Jezero Mons, there is a lower density of them than the surrounding terrain. So it's not just an ancient hill. There's something distinct about this hill from the rest of the surroundings. And another possibility you can have, if it was an impact crater, sometimes impact craters, their ejecta will kind of armor the surface against erosion. So you can be left with a crater sitting on top of a hill that's not just coincidental. But we don't think that's the case here either, because the sort of the profile shape is not really quite right. And if you armored the surface with relatively resistant ejecta, it shouldn't have a lower thermal inertia and it shouldn't be less cratered than the surroundings, we wouldn't think. So again, the evidence seems kind of most consistent with a stratovolcano. I would say we can't prove that it is that, nor that material from this construct got all the way to the opposite side of Jezero crater and could explain, would be the direct source of the rocks that the Perseverance has been busy caching. But if you know, what's a better guess, I guess, is the question I would ask. What more obvious volcanic feature is there that could have supplied these volcanic rocks in Jezero crater? So that's one thing we've been working on. The paper really should be published by now, but I made the foolish mistake of making myself the corresponding author instead of Sarah, who was just a sophomore when she started the project. And as discussed previously, I've had a lot of life events in the past few years that have slowed down progress. But we're close to getting this paper out so that hopefully people will start talking about the volcano on the rim of Jezero crater. In the meantime, I think it has been emerging that there are missing volcanoes from our geologic maps of Mars in other regions of the surface. And it's certainly a question worth asking. Like, I was only remotivated to look at this feature because we sent the multi-billion-dollar Perseverance rover 50 kilometers away. How many more ancient volcanoes are there on Mars that we haven't recognized just because nobody has been studying that part of the planet in much detail? And again, this is kind of an emerging theme in recent years. So about 10 years ago, there was a paper on the Arabia Terra region of Mars. This is one of the oldest, most heavily cratered regions of Mars. And so for many years, any roughly circular looking pit across this vast swath of northern hemisphere Mars was just assumed, oh, that's one of the many impact craters in this region. But some colleagues in 2013 published this paper pointing out that some of the depressions in this area really, like this one, I would say, really are not at all circular. And they kind of focused especially on this one, Eden Patera, which maybe it's sort of two superposed circles. But if you look in detail, they lack the raised rims that impact craters should have. A lot of things don't quite line up with an impact explanation for these depressions. And so they argued that these are calderas of large subsurface magmatic constructs, kind of similar to what you have at Yellowstone here in the US potentially. And then to kind of follow up on that, a few years ago, there was this paper that got a lot of press using the CRISM instrument on MRO to try to test this hypothesis. And so this is a press release. This is the actual paper, evidence, stratigraphic evidence for explosive volcanism in Arabia Terra. And what they did was compare to a model assuming certain atmospheric conditions on ancient Mars that said if you erupt this much ash from Eden Patera, that pit on the western part of the North Arabia Terra region I was just showing, how would the atmospheric winds be predicted to transport it? And You get a lot of deposition of hypothesized ash right around the North Arabia Terra region, but because of the prevailing wind direction, you get this long tail of deposition quite far to the east, is what they argued. And so then they went and looked for evidence of such ash. And again, it's quite far to the east that this extends, actually, provocatively, all the way over to the Nili Fossae region where Jezero crater is. And so this paper in 2021 was basically arguing that a lot of the alteration minerals, phyllosilicates, hydrated silica, again, extending even as far as where Perseverance is currently sampling, might be altered volcanic ash that originally came from Arabia Terra. So again, they're looking for things like hydrated silica clays that could have happened after water altered the easily altered ash that came from a volcano. So again, they're trying to answer this question, how did all this get here for, I would say, an ambitiously large part of Mars? People had previously done, detailed geologic studies of many of the subregions within here. So what, again, Dr. Rivera Hernandez and I wanted to do, working with another student, Grace Fanson, who was an undergrad here, now is a PhD student at MIT, was look more directly, more closely around Eden Patera and the surrounding mysterious pits and see that you should get the most deposition of ash, according to these models, in that area right around the calderas. So Grace went looking for that, and the map here shows all the letters are places that she found hydrated silica. So importantly, maybe most importantly, I would say, including within this caldera itself, she found this spectral evidence for potential altered ash supporting a volcanic interpretation of that caldera, and then got slightly better spectra, and we'd have more data, actually kind of surprisingly, from a feature, what is that, like 100 kilometers, 200 kilometers away. Again, it's a depression that I guess the default assumption would have been it's an impact crater, but doesn't really have a raised rim like an impact crater should have, has some weird kind of collapsed textures in its interior. And when Grace mapped the mineralogy here, she saw a lot of pyroxene, again, an igneous mineralogy phase. But then the evidence for alteration silica and phyllosilicates, and what I've now been trying to do with this newer camera on an ESA spacecraft, Cassis, is get better color visible imaging coverage of many places across this region, actually, because tragically for my science, I've been talking about CRISM multiple times. We lost CRISM a few years ago when the coolers for its infrared detector would not work anymore, and you get too much noise from an instrument itself, an infrared sensing instrument typically, to get interpretable spectra from remote sensing. So we have to use other tools to map things like this now, and so that's kind of ongoing work, even as Grace herself has moved on to other things now, trying to map with high resolution visible imagery, stuff that looks similar to the silica-rich deposits that Grace found and that these other authors were interpreting over a broader region. So the thing that Grace sort of focused on for her project, though, was interpreting the spectra in detail. And while the previous paper on this had sort of just said, there is hydrated silica, there are clays, those can form from alteration of ash. There are some minerals, and silica happens to be one of them, where you can form what we would broadly classify as hydrous silica through a number of different mechanisms, different types of opal. Volcanic glass can have broadly similar spectral features, but if you look closely at the positions of the minima of the absorptions in the spectrum, where the light is being most absorbed by the surface, and even at the curvature of some of the absorptions in the spectrum. I think this is the only couple slides I'm going to actually make you look at spectra, so for those of you who don't love them as much as I do. There are ways to quantify the curvature of the shape of the bands. This is called the concavity ratio criterion, quantifying how the curvature of that absorption. And previous authors had shown that if you take different types of silica from the earth that formed in hydrothermal versus low temperature weathering environments that are more amorphous versus more crystalline, they have different values of these curvature parameters and of where the minima for the absorptions occur. And others have looked at this in the Mars context and found that indeed silica that you find in interpreted volcanic calderas on Mars plots in a different part of parameter space from silica of different origins, sedimentary origins, et cetera. So this is what Grace wanted to try to do, to tease apart how does the silica in this region look like it formed in a high temperature volcanic setting. This is her big table from a paper that she's hoping to submit any day now if we get her feedback on it. Again, I'm holding things up, but things to call your attention to. So Grace also looked at the thermal inertias across this region and found values in the low 200s of typical thermal inertia units, which I'll just assert are again consistent with fine particles like you'd expect for volcanic ash. They actually also decrease the farther away you get from Eden Patera, which is consistent with the finest grained ash particles being able to be transported the farthest through the atmosphere. And then that one site B that was quite close to Eden Patera has spectra in particular that plot in the hydrothermal part of the parameter space, so evidence for a high temperature origin. And then just in terms of how they compare to other materials on Mars, a lot of these have the same properties as silica on Mars that we have found in more obvious volcanic contexts. So all of this, I would say, supports the volcanic interpretation for this region of Mars. So again, more previously unrecognized volcanoes. Now, even this is a pretty broad region. I would argue that Grace was looking at, and probably not, this table is heterogeneous in its entries, and that's probably because not all these things formed in exactly the same way. And in particular, if you look up in the northernmost points that Grace looked at, there have been other Mars scientists looking at similar materials in the northern lowlands of Mars, finding silica around things that they've been interpreting as mud volcanoes, those sedimentary constructs I talked about, and interpreting as evidence for relatively late in Mars's history of wetness, aqueous activity in the northern plains of Mars. So this probably a different thing from the volcanic story of North Arabia Terra, but is a nice segue into the next thing I wanted to talk about just a little bit, which is aqueous minerals and their relation to obvious sedimentary landforms on Mars, which has been a little less closely tied in practice than we might have imagined. So here was another project that PhD student Emmy Hughes just got published, looking in what has been interpreted as the largest sea other than a potential northern hemisphere ocean on ancient Mars, this Eridania Sea in the southern highlands of Mars, maybe the largest sea at one time on Mars, a lot of authors have said. And so Emmy went looking at the silica in this basin using the same kind of spectral analysis as Grace was doing, and just trying to confirm, like, is there evidence for substantial water rock interactions in the types of silica that are seen here. And she found basically the opposite, that oops, I froze. Yeah, okay. Right. Unmute myself now. I don't know what I changed. This is mute. Oh, there. Yeah, okay, thanks. Sorry if there's been an echo the whole time because I didn't realize that my volume was off. So anyway, yeah, Emmy found that most of the amorphous silica in Eridania was actually consistent with low to minimal water rock interactions. Doesn't mean there wasn't ever a sea here fed by hydrothermal circulation in the subsurface, but the evidence isn't all aligning. And we've seen this before, actually kind of one of the major, I think the most cited, actually I think this might be the most cited Mars science paper that there is, came out right at the start of my PhD, based on the previous infrared spectrometer in orbit around Mars, Omega, found both clay minerals and sulfates for the first time on Mars. And one of the striking findings that this paper reported is they were not in the locations we might have thought they would most obviously be, that is spread around the obvious large dry valleys and channels that we thought water had carved on ancient Mars. And so that was kind of a qualitative observation back then. There was a PhD student at Brown a few years ago who actually tried to quantify this and found there was an anti-correlation statistically between where you saw hydrated minerals on Mars and where there were channels. So that has opened the door for some folks to say, like, the channels on Mars were all carved by lava. It was like, this wasn't flowing water after all. And I think that is a step too far. And so I'm kind of trying to push back on this a little bit, because I think there are a few locations where we can find both pieces of evidence simultaneously, both mineralogic and morphologic, for flowing water on the surface. And this goes back to actually my PhD work. This is an outflow channel, Shalbatana Vallis, that has a basin along its stretches where water would have ponded for a while, even after the floods had stopped. And it looks like there's a sedimentary fan interpreted as a Gilbert type delta sitting adjacent to some light toned layered deposits in this long valley basin here that I took a look at in graduate school, found both sulfate salts and clays there. Still haven't published it. This is another project I've been returning to recently. Thankfully, we have new tools now, like PSAS, that can both image the whole deposit here in stunning color, and then show us that farther along the outflow channel, you can find other smaller exposures of what look like layered sediments along this long interpreted as fluvial channel, but some people had started to say maybe it was just volcanic, and I think this argues against that. So the latest thing is, in the past couple of years, I had a student, Colin Burnett, and a couple students before him actually looking at some of the other outflow channels surrounding the Chryse ancient impact basin on Mars. And here's one called Casey Vallis that has some light tone deposits near where it empties into the Chryse basin that turn out to have a hydrated silica spectral signature. Another one called Maha Vallis has something similar. Maha is actually directly upstream of where the Viking lander landed on Mars. Again, they landed there because they thought this was a fluvial channel that would have deposited sediments, and then the lander didn't find any, and it was a big disappointment. And again, everybody started thinking Mars was just volcanic forever. But if they'd just gone a few kilometers upstream, there's some nice juicy chemical sediments that they could have analyzed. And so we're trying to, again, get a paper submitted soon to tell this story, which has become even more timely with the news that apparently the Chryse Basin is the leading candidate for the Chinese sample return mission that I mentioned earlier. I don't know that they'll happen to be close enough to any of these spots to get some of these materials, but we should get the story out there too. Now, one final thing I'll throw up on the Mars topic is just, I'm excited to have a new student in the group who has previously published work showing that there are examples of this on the other side of Mars from the Chryse Basin as well. Another notorious place that NASA went looking for evidence of sediments that formed in ponded water, Gusev Crater with the Spirit rover at the end of this long outflow channel, Ma'adim Vallis. They found mostly volcanic rocks for at least the first long part of the mission. But as Tuhi has shown, there are places along this channel as well where you can find clays in layered deposits. So again, we just weren't looking in quite the right places. All right, so to briefly tell you about this new topic that I have been working on, which you might ask, why am I doing this? It's very different from where all my existing funding comes from and what I have most experience doing. I'll say in part, this talk is somewhat modified by, I was invited by a former PhD student, Luju Ocha, who did great Mars work here with me, now as a faculty member at Rutgers. I wanted to let him know while I was there that students like him who, he's now branched out to, he's publishing papers about Kuiper belt objects and IO and a wide range of things beyond his expertise developed in grad school. So if he can do it before having the safety of tenure, then you'd think I should be able to. Also, I also think it at least has the potential to be a major topic in planetary science in the very near future. So there aren't that many people working on it now because there have only been 2 of these interstellar objects found passing through our solar system so far. But in about February, this observatory in Chile is going to turn on, and there are predictions that it should find at least one of these per year, maybe much more than that. We don't know until we start getting the data. But this is also, as Francis alluded to, going back to my roots from undergraduate studying astrophysics at Princeton with telescopes. So I kind of always wanted to find a way to use my, dive deep into the planet that we arguably know the best beyond Earth, Mars, and then can I somehow use insights from a career doing that to help understand exoplanets, which are so much more numerous, although we have much more limited information about them. And I thought it would look something like this. This is some work by a colleague / rival. I was kind of disappointed that she beat me to doing this sort of thing, thinking like for the various types of minerals we have here on the Earth and have started to find throughout the solar system, what would we best be able to distinguish with the capabilities we're planning for upcoming telescopes to look at extrasolar planets, and you can tell planets that have like granites on them and thus maybe plate tectonics from planets that don't, and all kinds of interesting things. So yeah, Bethany beat me to that as with many other things. But then this totally unexpected thing happened in 2017 that an object that if you tracked its trajectory and velocity back came into the solar system at high enough speed that it must not be bound to our sun, and then came closer to the sun than even Mercury orbits, and fortunately for us, happened to pass pretty close to Earth on its way back out of the solar system, and turned out to be quite weird, but was a piece of exoplanetary matter delivered to our own solar system. So again, this first one, which is named Oumuamua, was quite weird. So it had colors sort of typical of a comet. This is just visible near infrared photometry, and it matches comets and sort of outer solar system asteroids, D-type asteroids. And it showed evidence that it was moving in ways that not just gravity could do, and so maybe sort of a rocket effect from outgassing like we have seen directly on comets in the solar system. But there was no coma of gas or dust surrounding Oumuamua that was detected. So that was weird. It was also weird that if you monitored its brightness over time, it varied dramatically in a way that led to some wild speculations, like maybe this is a tumbling light sail created by aliens beyond Earth. The fact that we can't definitively rule that out, I think, is argument enough in itself that we need to understand these objects a little bit better. But there are natural explanations, I think, as well. Like it would have to be a very flat or very elongated body to look as bright and then as faint in this periodic manner as it does. You can also see it's not quite regular, the period here, so it was tumbling in a chaotic way as it came through. And then, there's the fear that it was just a one-off thing, but then less than 2 years later, we found a second one of these. It looked totally different. It was clearly a comet. It's gotten kind of a bad rap that it was just a normal comet. It really was not a normal comet. It plots in a totally different part of chemical parameter space from any solar system comet. We couldn't measure some of the same things for it that we could for Oumuamua because it had this bright coma kind of shrouding its nucleus. So we don't even really know what is the size of this second one. How fast was it rotating? Was it rotating periodically? So what I've been doing this year is starting a collaboration with Karen Meach, who led the discovery paper on the first interstellar object, Oumuamua, and has some unpublished Hubble data for Borisov to see if we can back out information about the rotation state and maybe even the size. Once the second one, Borisov, got farther from the sun and its activity diminished, can we actually see its nucleus? Which would be super helpful because as we're trying to estimate how many of these there are and what the size distribution is, we basically only have upper limit type constraints for Borisov, and those aren't even that good so far. And, but as it is, it sort of seems inconsistent with population statistics we would have predicted. So it would really help to have two measurements there. But again, it goes back to the theme of how did these get here, and does how they got there tie to some of the unusual properties in certain ways? So did something happen to Oumuamua on its way from its system to ours that is responsible for its weird flatness or elongation? We don't know, but if we can measure a few more of these, maybe we'll be able to test between these kind of hypotheses, which would teach us a lot about planet formation. Even if we don't ever figure out which, a lot of people say like, well, how are you going to figure out which star it came from? I would argue that doesn't matter necessarily in the same way that we don't have to know where Mars meteorites came from to know that they're, to learn about Mars from them. So why this gets my attention is because I'm a person who does a lot of mission science, and if these things are actually passing through the solar system at a non-negligible rate, then maybe we could actually send a mission to fly by one and resolve the nucleus directly. Is it elongated? Is it flat? Does it have impact craters? All kinds of questions you could readily answer with a simple image. And then the composition of Oumuamua is sort of totally unconstrained. Any kind of chemistry sensing instrument could give you way more information than we were able to get with telescopes. So this would be a challenging mission. Every time I try to talk to engineers about this, they're like, do you have any other mission concepts you're excited about besides this? And I have a few counter arguments to that. First of all, Earth has done this before, maybe not NASA, but ESA did a very high speed flyby of the most famous comet of all in 1986. It's the same thing as like, well, it's too hard to land humans on the moon. Come on, that has happened, I'm pretty sure. So, and also simultaneously, ESA is planning a similar thing again. So one challenge with these is like, you have such a limited warning, like you detect it and then it's going to pass by closest to the sun and be back out of the solar system in just a few months. ESA has figured out a plan for that too, and is going to launch a mission and just wait for an Oort cloud comet to be found. I think we could do the same thing with interstellar objects. So final slide, just to if you're still not motivated by this, and it's worth pointing out that it's not surprising that these things exist. In fact, back probably before many of you were born, 1989, there was this paper written saying it's surprising that we don't see any interstellar objects in the solar system. What's wrong with the galaxy that it hasn't sent us any yet? So it's not that their existence is surprising, it's that their properties are very different from solar system asteroids and comets. And to me, that reminds me of when we were finding the first extrasolar planets, and they were hot Jupiters, which is a kind of planet we don't have in this solar system. And it sort of opened our eyes to the fact that maybe planets don't always stay where they first formed, and that ended up being a pretty impactful discovery. So I hope that we have more of these to study in just the next couple of years. Here's all the things that I talked about. Happy to answer questions about.